Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show an application of conjugate heat transfer analysis using SolidWorks flow simulation. We have already shown this type of conjugate heat transfer analysis, but this is completely different type. In this case, we are utilizing one heat pipe which is made up of copper, and inside these copper tubes, very small amount of water will be there. We know that already the heat pipe can be divided into three different temperature zones. First one is this is known as evaporator zone. Second one here will be the adaptive zone, and the remaining one is known as condenser zone. You already know that in heat pipe the temperature difference at the different zones are very less amount because thermal conductivity of this heat pipe is very high compared to normal copper. In this case, to maintain a huge temperature difference between the evaporator zone and the condenser zone, at the condensation zone we have provided one metallic plate which will be kept at a lower temperature. In this case, the lower temperature will be 5 degrees centigrade. In this analysis, we have tried to consider different specific zones, that this is point number 1, 2, 3, 4 different zones we have created. As a point goal, we want to have temperature at different locations, and that will be obtained using point goal. So without wasting time, let us start our simulation. It will be started from simulation itself. Here, environment of flow simulation will be initiated with wizard itself. We're keeping the name of the project as default project 3, and next to that, the unit system we have to select. We are selecting the unit system as SI, and pressure will be in bar and temperature will be in degrees Celsius. Next to that, it will be an internal analysis. We'll consider heat conduction in solids from the physical features, and gravity will not be involved because the thing is, it is very less height is there. It will be actually on the XY plane, on the ground plane. So next to that, we have to select fluid. Inside these copper tubes, it will be very little amount of water will be there. So we're considering water as the default fluid. Next to that, we're using two types of different materials. Copper tubes will be there for these heat pipes, and aluminum alloy 6061 will be for the cold plate. So from here, by default, we'll take copper, and the remaining material will be provided during applications of boundary conditions. Next to that, the default outer wall thermal conditions and roughness we are considering, and actual values will be provided during application of boundary conditions. Next to that, you can see the pressure is 1.01325 bar, temperature is 20 degrees centigrade. Similarly, the solid parameters, it will be also 20 degrees centigrade. Let us finish this. You can see this is the computational domain. We can hide this domain. Next to that, we have to select that fluid domains. That means through these copper tubes, water will be flowing. So we can select fluid subdomains. Insert fluid subdomain to be water passing through these copper tubes. Select other. So you can see that this is the fluid subdomain or fluid domain of water. You can check. Next to that, we have to provide solid materials. Because two types of solid materials are there. One will be copper for the heat pipes, and the cooling plate will be made up of aluminum 6061 alloys. Okay, solid materials. Insert solid materials. Predefined. It will be metals, and we are selecting copper. For selecting that material, we can select it from the geometry itself, and solid bodies. You can select the different zones as evaporator zone, adiabatic zone, condensation zone, and also the compensation chamber. This one is the compensation chamber. We have selected all these things, and that will be made up of copper. You can check. Is done. Next one, we have to select this one as a aluminum plate, which will be providing less amount of heat. It will be kept at a constant temperature of 5 degrees centigrade. So solid materials, insert solid material, predefined alloys. It will be aluminum 6061 alloys. Let us select the plate, selected, grain check. So material has been defined properly. Next to that, we have to provide specific properties of heat pipe. You can select from conditions. It will be heat pipe, and for selection of heat pipe, initially you have to select all sections. From here you can select the geometry, that is evaporative section is selected, then adiabatic zone, and finally the condensation zone or condenser part, and also we have to select that compensation chamber also selected. Next part, here we have to select that heating zone. Heating zone, that means we want to provide heat at this location only, so we can select this one as a heating zone. And finally that condensation zone, that means where we are providing cold plate. So this is the condensation zone. You can select the specific location for condensation zone, selected. And next to that you have to provide effective thermal resistance. This one is actually experimental property, so this value will be in this case 0.11. In our goal also we'll check the value of effective thermal resistance. You can check, it is provided. Next to that you have to provide heat source, that will be coming from conditions. It is surface source, and this one will be providing heat at a rate of 500 joules per second, that means it will be 500 watt. You can check. So it is ready. Next one, we have to select some goals, right? So goals, insert surface goals. Initially we want to have surface temperatures at different zones of the heat pipe, that means evaporator zone, adiabatic zone, and condenser zone. We'll try to find out temperature at different zones, and also with some specific points we'll try to find out point goals. So initially we're trying to find out surface goals. Insert surface goals. When you have average temperature of fluid at different zones of the heat pipe, it will be average temperature of fluid at different zones of heat pipe. You can select the different zones from the geometry also. Evaporator zone is selected. Next one, we want to select that adiabatic zone, and finally we want to select that condenser zone, and again that compensation chamber also we want to have. And we want to create goals for all these different sections as a separate goal. So create goals for each surface separately. Done. We have made different goals. First one is the temperature at the evaporator zone. Second one is the temperature at the adiabatic section. Third one is the temperature at the condenser zone, and fourth one is the temperature at the compensation chamber. Excluding that also, we want to find out some goals as point goals. Insert point goals. In this case also we want to have average temperature of fluid at a different point locations. So these are the points. This is point 1 we have already created before. Number 1, this is the temperature at the adiabatic section. This is point 3. Point 4. Point 5. At different extreme locations we have to find out temperature as point goal. Selecting different locations. So we have selected 13 different points. At each point, we have to find out temperature, right? Okay. Selected, green check, selected. And also one thing we have to do, we forgot to do that one, that is we have to maintain the temperature at the cold surface to be 5 degrees centigrade. That can be obtained from the boundary conditions. Insert boundary conditions. This one we have to consider as walls, and let us select that walls. You can select it from the geometry itself. That means cold plate we have selected, and that will be maintained at a temperature of 5 degrees centigrade. You can select this one as constant temperature of 5 degrees centigrade. Selected, green check. So the cold plate will be providing temperature. Always it should be 5 degrees centigrade, right? So we can review this again. From the heat pipe, from this surface will provide heat at a rate of 500 joules per second. This is the evaporative section. From here water will be passing, and this is the adiabatic section. Here temperature will be a little bit less, and finally it is coming to the condenser zone. And again the condenser zone is attached with a cold plate which is maintained at constant temperature 5 degrees centigrade. Therefore we can visualize very less temperature at the condenser zone, right? So with this conjugate heat transfer analysis, our aim is to see temperature at different zones, and with this conjugate heat transfer analysis, our aim is to see the temperature at different zones through different goals. Initially, we're trying to find out the goals as surface goals at different locations of the heat pipe, and finally, we want to see the temperature at different specific locations at point goals. Okay, so we can start our simulation right now. We run it, running the new calculations. The iterations have already started. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis. Okay, simulation is over. Now you can see our results are converged. We got all the results are converged, and from the goal plot we can see the average temperature of adiabatic zone is 29.12 degrees centigrade, and the same at the compensation chamber is 33.44 degrees centigrade. And similarly you can see that temperature at the cooling zone is little bit more compared to 5 degrees centigrade, as it was maintained at a constant temperature of 5 degrees centigrade. Now you can see very little rise in temperature, right? Let us close these things and we can see the results from the different cut plots. Okay, now you can see the results from here. Results. First we'll see cut plots. Insert cut plots. You want to see results from top plane. Let us select that plane. It will be top plane, and you want to see temperature of fluid from top plane. Can check. So for viewing the flow particles inside this one, we have to make the model completely transparent. Let us make the model transparent. Let us select this model from the geometry itself and we'll make it transparent. It is transparent right now. Now you can see the temperature at different zones. You can see that temperature at the evaporative section is very high. It is in the range of 60.29 degrees centigrade, as from here we are providing heat as the rate of 500 joules per second, and as it is approaching towards the adiabatic zone, its temperature is reducing. In the adiabatic zone, its temperature is in the range of 27 to 38 degrees centigrade, which is indicated by green zone. Next to that, it is coming to the condenser zone. At the junction of condenser zone, its temperature is blue zone. That means its temperature is near about 16 to 27 degrees centigrade, and as it is approaching towards the cold plate inside the condenser zone, its temperature is in the range of 5 to 10 degrees centigrade. You can see at the condenser section there is huge loss of heat, as there is a cold plate which is maintained at a temperature of constant 5 degrees centigrade temperature. Okay, let us see something else. Let us see the pressure also. Pressure, you can see almost similar pressure. Pressure is not that much change. Okay, next to that we will see the surface plots. Clear and hide these things. We're going to see surface plots. Insert, it will be temperature of fluid, or you can see the temperature of the solid also can check, because surface should be made up of solid. Let us see the temperature of the solid surfaces. Use all phases. It is the same representation if it is solid or fluid. What we saw in our fluid case, it is exactly the same thing. That means temperature at the evaporator zone is very high. It is in the range of 60 degrees centigrade, and as it is approaching towards the condenser zone, its temperature is reducing. Let us clear and hide these things first. Surface plots, clear and hide. Next to that, we want to see our goal plots. Insert goal plots, and we want to select all the goals, and we can see all these things in the form of graphs also. Let us see these things. Show. These are the results which we have already seen from the solver window. It will be easy to understand from the graphs or history. Let us see the results from the history. It will be represented in the form of graphs. You can see here the minimum temperature of fluid is 4.85 degrees centigrade, and maximum temperature of fluid is 60.27 degrees centigrade. And next to that, we are having temperature at different zones, that is obtained at different locations. First one is temperature is 33.33 degrees centigrade. At a different point goes, we got it right. So these are the results obtained at different locations of the heat pipe. If you want to see these things in a better way, you can transfer these things in Excel and check the results, right? Let us see these things in the form of Excel. We can export it to Excel and check the results. These are all the data. We can transfer it to graphs. First one, we want to see the effective thermal resistance. This one is an experimental property or experimental value. We decided this one to be 0.11. Let us see how much is the value here itself. Effective thermal resistance. Okay, you can see the after 350 numbers of iterations, the final value of this effective thermal resistance is 0.11. It is exactly right what we got in case of our experimental value, and the goal plot, it is providing the same thing. Next one, we'll see the average temperature at the compensation chamber, which is the symmetric part of the adiabatic section. Let us see the temperature at the compensation chamber. Again, after 350 numbers of iterations, the temperature at the compensation chamber is 33.4 degrees centigrade. Next one is the temperature at the adiabatic zone. It is in the range of 29.12 degrees centigrade, because this adiabatic zone and the compensation chamber are on symmetric positions, symmetric locations. Okay. Next one, we want to see average temperature on the evaporator. It will be very high value, because from there only we are providing heat at a rate of 500 joules per second. So temperature at the evaporator zone is 59.46 degrees centigrade. Next one, we want to see the temperature at different locations of the heat pipe. those are obtained as point goals at different points we have selected. Point number 13, 14, 12. So 12, 13 numbers of points we selected. Let us see the temperature at the different point goals. First one is the temperature at point number 13. It is seen its temperature is after 350 numbers of iterations. Its temperature is 8.93 degrees centigrade. These are the different temperature zones. Okay, now we can close these things. So this is our analysis regarding conjugate heat transfer analysis of a heat pipe using a heat pipe and one cooled plate which is maintained at a constant temperature 5 degrees centigrade. Okay, instead of stopping it here, we can go for some kind of parameter study in which we can change the wattage of this heat surface and see the variations of temperature at the different locations, right? And from this parametric study we can select our results as per our requirement. Okay, thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.